will like cut off your
Hold on. I thought you would be here like 10:30.
I know. That's in the middle of the episode. I walked those over as fast as I could. And dying. Why do you
It's
see
been a
picture?
week since I've even looked at it.
Yeah.
I think it's because I just effortlessly. Oh no. Not like
Just do all of it in like 3 weeks.
like I've seen worse.
Yeah.
Actually,
But still like
what do you sign?
pretty bad.
Oh, so you
Yeah.
Get it out. It's just so
be
funny.
like,
Okay, I'm sure.
yeah.
No, I would've. It's not like the food natural.
I can just do, wait, you didn't even do the sound
Well,
homework?
usually I, like if I was gonna be absent, usually I know in advance. Like I got sick, it'd be one thing, but.
And that's what I was thinking. You were really sick yesterday. So my brain was like, oh, wait, she's sick. Come in today.
Yeah. Actually, surprisingly fun. Okay, so far today. But instead of going to calculus, I went and got medicine for my mom.
I still came at the usual time, but it
Well, I got here.
finish the lab that I just finished.
Yeah.
But I didn't put it in the backpack.
Is it like a
So I thought I'd pull
requirement
something else
that?
on my computer. I didn't bring my laptop.
Does that?
Dang.
Because I had asthma attack. I was thinking barely. I was rushing to go to my friend's car because she's so fast. She
Yeah.
needs to be there.
Well, I got here at the same time. Well, I arrived early, like, and like, but it canceled because I was back in the car.
Wait, what does it
and got
say?
back done.
Well, it has just some
And then I took
information
me to
about
watch
like different
TV
oils, and
for
it
an
does,
hour.
it does recommend olive oil, but then it like also
Then I
recommends
parked kind of
you
frankly
take
because
like
it's hard to see.
vegetable, corn,
I
flax
hate
oil,
driving in at this time.
which are all like
It's right at
spoiled
park,
before
and
you
freaking
use the
like,
process.
it's just so pretty.
Yeah.
The glare, and I'm like,
And then it like cuts down like animal fat.
When was it
That
made?
health science,
It's
more
probably
like,
like-
it's more like astrology than that.
You got this.
Thank you.
oh, yes. What's your music?
Do I get extra credit?
1 point.
You might get your wish, Marissa. Look at the psilocybin and psychedelic mushrooms for the research paper. So I'm trying to find good articles with like the mechanism behind it, like anti-anxiety and like.
Yeah, that would be cool.
But a lot of them are like, a lot of the articles I've found so far, it's like, oh, and here's how we made like analogous molecules that don't have as long of like a hallucination.
Oh, that's cool too.
Yeah, they're trying to like take out the long hallucinogenic effect, but keep like the therapeutic anti-anxiety.
Yeah, that was interesting. And that'd be good too, because then you can, because I always like showing molecules, especially we can show like families or classes and be like, yeah, they're doing all these little modifications.
Yeah, well, all the psychedelics are so similar, they're all based on the dimethyltryptamine group, basically.
Yeah, exactly.
Like, they're all just different groups added onto that.
Yeah. And that's, I mean, you can already see how drug development essentially works. Like, that's research, you know, you like, yeah, start with something, let's change this arm, and.
Yeah, let's see what it does.
Yeah, exactly.
What was that about?
Okay, so that's not for next week, but then I have my other biology and then my chemistry exam back to back. And I have my music midterm is the one that I have.
Never seen it in my life. It's very important. Quickly.
Yeah, this is my quiz this week. And our lab Tuesday. And the next day I have my biology exam and my practice on, and then after that I have my lecture So, yeah, so I'm just like, I'm probably going to
Access, like, this article, because I can only see the abstract on there.
Just email it to me.
Email it to you?
Yeah.
Okay, and see if we can get it?
Yeah.
Okay. Well, it's just hard because, like, without reading the rest of the article, I don't know if it's one I want to do.
Oh, it's fine. It's, yeah. I expect that. Yeah, it's better. At least you're starting early. That's why it's like better to start early too, because it takes so freaking long to try to get access.
I don't know.
When I'm in ACS, I don't need to have, like, a
Yeah, that's fine.
Good.
All right, let's go ahead and get started. So I think some of you saw this walking in, but today is Oregon Transfer Day. Does anyone know how long they're going to be down there? Okay, so until 1 p.m. So I would try to check it out, especially if you're transferring. And of course, right, if you're not interested in transferring somewhere in Oregon, you know, your college is not here today, definitely, you know, feel free to talk to me, or if you want to explore, like, transferring to other places. It's not that big of a deal, right? You just have to reach out to the university, start a dialogue, get an advisor on board, and start that. So check that out. Any other announcements? I think we have club fair next week. Do you want to? I forgot what days they are. So.
Yeah, it's actually, the clubs for next week for Riverside campus is going to be on Wednesday. It'll be from 12 to 2 p.m. And we'll have all sorts of different clubs. Earth Club, you're already on that, right?
Yeah, we're going to.
And we'll have Saga, I believe Martial Arts Club, Music Club is going to be coming, Engineering Club. So we'll have quite a few different clubs present. It'll be a nice fun event. So yeah, thanks for giving me the opportunity to show you.
All right. Any other announcements or things we need to talk about before we dive into it? I'm slowly making my way through your grading. So I've graded like half the labs I received, but I did not put the grades in. I'm still missing extra credit. So hopefully today I'll work on that. All right. So we left off with Dalton's law of partial pressure. And so let's just reflect on this, right, where we were. So we were saying our moles are additive, so this might be helpful. And again, that moles is related to our pressure. And then we said our pressure was additive to give us our total pressure. And so we had gone through our mole fraction. So this is important, being able to figure out our mole fraction. And then we can use our mole fraction to figure out our partial pressure. And so, right, we were looking at our example of air. So we said, well, air was 78% nitrogen, 21% oxygen, and 1% argon. And so that translated to those amounts below. Oops. So let's try this practice problem then. So we have a 1 liter mixture of helium, neon, and argon, and it has a total pressure of 662 millimeters of mercury at 298 Kelvin. And so the partial pressure of helium is 341, and the partial pressure of neon is 112. What is the mass of argon? So start walking me through. So how far did we get on this one?
The first thing I did, I'm not sure if this is right, but first thing I did was see that the total pressure is 662, and then I minus 341 and 112 from that to get the partial pressure of argon.
And so what was that number? Sorry, I don't have my calculator.
209.
So it sounds like other people got that as well. So everybody made it this far then. And so what can we do now? So, okay, we have our pressure, but it's asking us for mass. So now what equation might be relevant?
We could use the isodecimal to get moles.
Yeah.
We have temperature and volume at a constant.
So exactly. So we have to look for those little hints. And so, yep, that brings us to our PV equals nRT. So now we have to do some converting. So our pressure, let me pull up my calculator. So then did we get 0.275 for the pressure in ATM? I see some nods, so 0.275, so ATM. So volumes in liters, that's good. And we're solving for moles, so I think we're ready to roll. So we can either kind of rewrite it. So I want to solve for N, so that's PV divided by RT. So R, I'm going to use the 0.0821. You could use the more precise value, 298. And so what do people get when we plug that in? So I get this number for moles, so I see some thumbs up, more thumbs up. Other people are punching. I'll write that, so 0.0112. And so that's moles of argon. And so if you make it here, right, that's pretty good. And then what's our last little step to get from moles?
Multiply by atomic weight of argon.
And what's argon's atomic weight, like 40? 39.93? Oh, 48. Argon's a noble gas, though. So 39 point. So then do we all get about 0.449 grams? So 0.449 grams. Excellent. Let's do another one. So let's do one from your book, because your reading question has kind of a tricky problem. At least every year, students always have questions on it. And your book has a similar problem, except they didn't go through the map. So I figured we could do that. I can copy my problem. So this is from the book, problem 1312. And so this is the flask separated by the stopcock. I could bring the picture over if that helps, but I think the picture could create more confusion. But let's see. Oh my gosh. Let me try that again. So we have our scenario. So we have two flasks that are connected by a stopcock. So one flask has a volume of 500 milliliters and has nitrogen at a pressure, oh my gosh, oh here we go, sorry, of 700 torr. The other flask has a volume of 400 milliliters and has oxygen at a pressure of 950, so there's our picture matching. And so if the stopcock is open, so the gases mix, what is the partial pressure and the total pressure? So do you remember how to solve this one if you did the reading quiz? If not, how would you solve it? So take a few minutes to work on it, and then of course we'll go over it. So how do we approach it? Any ideas of what we could do?
I guess you could start by analyzing what things are constant, what things aren't constant, whenever calculating the partial pressure. In this case, the temperature and the molarity is constant, whereas the total volume that the different gases have to occupy relative to their original temperature, the partial pressure changes, and the pressure, of course, will be changing as they occupy that new volume that they, I guess, will open up as they mix. And that's about as far as I got after the setup. I was moving into, of course, the relationship pressure 1 times volume 1 equals pressure 2 times volume 2.
Oh, excellent, yeah.
And
Nope, that sounds completely correct. So let's go over that again in case you didn't hear, and so we're all on the same page. So it's easier to kind of treat it, right, as a separate kind of volume change problem. So, right, just one of these issues. So let's just ignore, well, let's start with nitrogen. So let's ignore oxygen for a second. So what our problem is really saying, well, we have nitrogen in a 500 milliliter flask, right, at 700 torr. But once we open it, now we have a total of 900 milliliters, right, with our volume. So then we're asking, well, what's our new pressure of our component nitrogen? So does that make sense how we can do that? And then we can repeat that, and then we repeat that, so ignore nitrogen, repeat that for oxygen, so same thing. We have 400 milliliters at 900 torr. Open it up to our new volume of 900, and that's our new pressure. And then, just like Alira said, then we can add those partial pressures. So let's walk through that all together now. And so, like I said, I'll start with nitrogen. And so that was kind of the other thing to recognize, that yes, our temperature and moles were constant, except our PV equals nRT doesn't help us, right? Because they didn't tell us what temperature. We just know it's not changing. Same thing with the moles. We know that it's constant, but we don't have an amount, so we can't use that. So that's why we're kind of left with this equation. All right, so let's set that up. So nitrogen was initially 500 milliliters at 700 torr.
Can I ask how we know that the moles are constant between these two?
Because it's a closed system, so they're not, nothing's, being added.
Okay, I see.
And so then we go from 500 to the 900 milliliters total, just adding, again, my total volume. So we're volume, so now it's 900. So let's calculate our new pressure. So double check my math, and if you're in the chat, I'm looking for answers as well. So I see thumbs up. So did we get 388 for our new nitrogen pressure? 388 torr. And so let's repeat that for oxygen. So again, just P1V1, P2V2. So same process, except starting with 400 milliliters at 950. And again, we still have 900 total. So let's solve for a new X. So do we all get 422 torr for our X? I see thumbs up. Everybody's still. So 422 torr. And so, well, it looks like we went ahead and calculated the partial pressures, and now we need to do the total pressure. So now we can, of course, just add. Make some more space. So 422 plus 388. So about 810 for our total pressure. Questions about this one? You feel okay about this? And so that's really the trick of our gas laws chapter, right, is what formulas do we have? What variables do we know? What's being held constant? All right, let's continue then. And so now let's at least talk about the concept of vapor pressure. And so we saw this in lab, right? So we did this. So we collected our gas by displacing water from a container. And so, right, we did this exact experiment where we collected gas in the eudometer. And so at the time, right, you just kind of plugged in all those numbers, but now we're explaining why it was relevant to account for the vapor pressure of water and, you know, why we just subtracted that. So of course, again, we just accepted it. And so what's happening, and so of course, we were collecting our gas, but then the problem and what we had to take into account is that even though we're not at boiling, right, a liquid still exerts some sort of vapor pressure. So there's still some molecules that are being evaporated, and so that means that there's going to be vapor pressure, and so of course we have to account for that confounding pressure. And so that's where I said, you know, look at this chart. And so basically what this is just showing, right, our pressure versus temperature relationship. And so you can see it's just increasing, obviously. So as our temperature increases, our pressure increases. And then look at what defines normal boiling point. So we'll probably come back to this concept later. But once your partial pressure hits the same as your atmospheric, so if we're in millimeters of mercury, now this is the temperature, which it hits 760. So, right, that's 1 atm. And so that means this is our normal boiling. And that's why we can say, oh, at 100 degrees, right, the vapor pressure is 760. So this is our boiling point of water then. And so that's also, we're not trying to calculate it in this case. We're just reading it from the chart just like we did, or we can, you know, ask Google. And so then the next bit of the chapter talks about the relationship of temperature and molecular velocities. And so we have that our average kinetic energy of our gas molecules depends on the average mass and velocity. And so that means that it's going to be the average of the squares of the particle velocities. And so gases in the same container have the same temperature, and so that means that they would have the same kinetic energy. And so if they have different masses, then the only way for them to have the same kinetic energy is to have different velocities. And so the key thing is that our lighter particles will have an average faster velocity and of course be more prone to escaping as well. So that goes back into, if you want to think about like how can we use hydrogen as a fuel, not only of course is it flammable, but it's an extremely light and tiny particle that has a very small velocity, and it can also, right, escape. So if you're thinking of like even just a balloon, right, hydrogen would escape faster than, you know, xenon or argon. And so with this formula, notice that your mass is in kilograms per mole, so that's to line up with our velocity. So if you wanted to kind of derive where this is from, you know, kinetic energy is 1/2 mv squared from physics, where mass is in kilograms there. So that's why we're in kilograms in this formula. So just note that. And then our R, I want to say this is our 8.314 R. Yes, I think it's, there it is. It's lower down in my notes, sorry. And so our kinetic energy, so when using this formula, our R is now our gas constant energy units of that 8.314 joules per mole, And then again, that's related back to velocity, right? Kinetic energy, 1/2 mv squared. So this is kilograms meter squared is our energy. All right, before we go back to the formulas, and so what are we saying? So, right, we're saying that we have our, so this is our distribution. And so now what we're saying is, so our lighter particles are going to have a wider distribution. And you have to think about what this is showing. So basically, if we have all our gas particles moving around, and then we just take, excuse me, take a snapshot of what is their speed instantaneously. So you'll have some, right, that just happen to not be moving. You have some, obviously, that this is kind of our average velocity. And then you'll have some anomalies that are obviously moving really quickly. And so the thing to note is hydrogen has a very wide distribution. Again, we have our lighter particles, and so some are going to be moving really fast. And then as we get heavier, their distribution just kind of tightens up a little bit. And again, the middle just kind of corresponds to then our average speed.
Can you go back to that constant real quick? To use that.
Oh, this one?
Mean square. Yeah, thank you.
Yeah, so now let's look at our formula. And so again, this is relating our root mean square velocity. So this is just rewriting our formula here, where NA is our Avogadro's number. And then we can multiply it. So this is Avogadro's number times our molar mass in grams per mole. And so we can see, right, as our temperature increases, then our velocity increases. So let's try this one. So calculate our root mean square velocity of oxygen molecules at 25 degrees Celsius. So let's see what we got. So we can plug it in to this formula. So our root mean square velocity is equal to 3 RT over our molar mass, and again, that was in kilograms per mole. And so that's kind of awkward. So that gives us 3 times 8.314 times 298. And then, right, our mass of oxygen is 32 grams per mole, but if we want it in kilograms per mole, then that's 0.032 kilograms per mole. So that's what we need to plug in. So that's the only kind of tricky part with this problem, is converting it. And what do we get when we plugged it in?
482.
So 482, and then that's our meters per second. So again, relating back to our energy units. Excellent. And so we can also calculate what's called our mean free path. And so all this means is we'll write, again, molecules, we just assume that they travel in straight lines until they collide with one another. And so then we can calculate the average distance a molecule travels in between collisions. So that's just our mean free path. And so going back to what we're thinking, so higher pressure means more collisions and more frequency of collisions, so then your mean free path would decrease as your pressure increases. Yeah, I don't think we do too many math examples of this. So there is an equation in the book, but I don't think we do examples of it. So other things that we care about are diffusion and effusion. So all this means is molecules spreading out. So of course, the process of molecules spreading out from a high concentration to low concentration is called diffusion. And right, you can think about either, well, in water, if you put some food coloring in, it'll disperse throughout, or thinking of gases, somebody can spray perfume in one side of the room, and then, right, it'll make its way throughout the whole room. And we also have what's called effusion. So this is when molecules escape through a small hole into a vacuum. And actually, they're usually called diffusion pumps, which is kind of funny, because they just use the term effusion. But these diffusion pumps help you get down to like really low pressures, so like 10 to the minus 8, 10 to the minus 9 torr or more. And so again, right, we have this thought that heavy molecules fuse more slowly than lighter ones. And so our key equation is this relationship. And so notice, right, the variables swap. So if we're comparing two molecules, so our rate of A compared to our rate of B is equal to the square root of B over A, and those are our masses. And so let's just finish up the last bit of the chapter, and then we'll maybe practice some other problems. And so again, we have our real gases, and so we've kind of been touching on this whole time, that real gases obviously behave differently from ideal gases, and often, right, our kinetic molecular theory breaks down at either high pressures or low temperatures, right? So at high pressures, now they're getting closer and closer together, so now those intermolecular forces come into play. Same thing with low temperatures. Now they're losing energy, so they will condense. So, right, both of these kind of force it to condense, so not ideal gas behavior. And so like we were stating, so again, we said that there were no attractions and that gas molecules do not take up space. And again, obviously, at low pressures and high pressures, those assumptions are not valid. And so this is the chart that I was thinking about when I was mentioning that, right, the true molar amount. So we said at STP that 1 mole of everything is 22.4 liters. And so this is just, in actuality, the deviation. And so you can just kind of appreciate that, right? We don't need to know anything, but just, yes, right, these assumptions break down. There's going to be deviation. Molecules do occupy space. And so all that is going to influence their true volume just a little bit, right? So, and they really don't even deviate that much. So kind of interesting. And so again, right at low pressures, at least for argon, the molar volume is nearly identical to that of an ideal gas. But of course, as the pressure increases, then the molar volume of argon actually becomes greater. And so again, it just depends. So at high pressures, the argon atoms obviously start occupying space. So it makes the actual volume greater. So you can't compress it. So that goes back to, right, the limits of compressibility. So again, their physical space comes into play. And so we could calculate this. So there's the deviation. So there are equations. And even in this class, I don't think we use it. You should at least be aware of it in case it comes up. But again, I don't think you'll use it too much in practice. But van der Waals did come up with a modification. And so, right, every gas would have this van der Waals constant, so that would be something that you would have to look up. And then you end up, right, with this equation for your corrected volume. Again, I don't think we'll use it in this class, but at least you know it's there, it exists. And so same thing with our intermolecular attractions. So again, we were saying, we assume there's no attractions, and at high temperatures, the pressure is similar to an ideal gas. But then, obviously, as you start lowering that temperature, we're losing kinetic energy, and so those intermolecular forces come into play. And so at lower temperatures, you find that the pressure of gases is less than an ideal gas, again, with those intermolecular forces. So now the gas atoms spend more time interacting, and right, probably they start to condense a little, and so it makes their pressure less. And so just like the volume correction, there's a intermolecular attraction correction. And again, this would be another thing, you have to look up this van der Waals constant to do that for every gas molecule. Obviously, right, that's probably something that was determined experimentally. And so this is, again, our corrected equation, which I don't anticipate us using too much. And so this leads us to this overall combined van der Waals equation, which again, I don't think we'll use, but handy to know that it exists if you ever needed it later. And so now this is just showing our behavior of real gases. And again, we can just kind of appreciate this. So our ideal gas, so this is, right, our PV over RT ratio. And so this should just be constant at 1, but then it deviates a little bit depending. So you can, again, appreciate, like, water looks pretty wild, but, you know, again, water is going to condense. And, you know, again, just look at helium, how that kind of tracks neon. How are we feeling about this chapter? I think that's everything. Yeah, I was going to do an effusion equation since we didn't do that. So let's go back to that equation. So we had this one. And so we have two balloons. And so nitrogen leaks out. And so our two balloons, so we have them filled with nitrogen and helium. And so nitrogen leaks out at a rate of 75 milliliters per hour. And so what is the rate then of leakage for our helium? So go ahead and try that.
And that refers to what, the atomic mass?
Yeah, the atomic mass. And then, yeah, don't forget that nitrogen's diatomic. How's our problem coming along? Oops, what happened to my thing? Oh, so weird. Okay. And so for this one, right, it doesn't matter who we call A, who we call B. So did you guys assign any of them, A or B?
To make it easier, so there was less dividing of the phone divided by friends, they might not be easier, but I assigned rate A as the rate of helium, and then rate B the rate of nitrogen.
So let's do that. So we'll just call helium A, it doesn't really matter. And so nitrogen will be B. So then we set up our equation. So then our rate of A over our rate of B, which we have, is equal to our square root of B over A. And so what's our mass of nitrogen, though? So 28.014. And then what's helium? Excellent. And so now it looks like we just have to start doing the math. So let's just solve for this first. And take the square root of that. And so now we have something like rate A over rate B is equal to about 2.65 or so. So then we can multiply by rate B, since we have our rate B for nitrogen, so times 75. And so do we get about 200 then or so? So, and then again, just be consistent with our units. So we were in milliliters per hour there for our helium rate. Any questions about that one? And again, you could have flopped A and B. You should have still gotten the same answer. All right, I think we're out of time, unless there's anything else that we wanted to go over. Are we feeling okay on examples? A little bit better? So let's go ahead and take our break, and then we will do our quiz when we come back. And so if you have questions about this chapter or previous chapters, we can continue talking. And I'll hang around on stream for a little bit. Does anyone want to take a picture of this? Because I realize I'm going to erase it for our quiz, because otherwise I might give too many answers away.
So I put helium.
Wait, why do you have 8 though? I think that's your only mistake. Because remember, helium's just 1 though, so helium is not diatomic.
Oh, that's
Thank you.
All right, am I good to erase this?
Yeah, no, I mean, I'm fine, I just kind of have a question as far as SP mixing. So, because I know what SP mixing starts with nitrogen, right?
Yeah, so nitrogen on down, so
But
from
is that-
nitrogen, carbon, boron.
So, but does that mean just any molecule that has, like, say, nitrogen up, or is it like diatomic? Or does it have to be
Well, we're basically focusing on the diatomic, so nitrogen down though, right? So nitrogen, carbon, boron,
So, wait, so those ones have mixing?
yeah,
Anything
oxygen,
above
fluorine, neon do not, yeah. Because their S and their P orbitals are too far apart. And then it gets weird, right, with like CO or NO, like how, and that's part of the computational chemistry question is like, how much mixing do you invoke? And then you do an experiment, you're like, what really describes it?
Okay.
But yeah, that's, for a non-diatomic molecule, like CO, I would say like invoke SP mixing or like, yeah, or maybe even do a comparison, draw one diagram where they are SP mixed, one where they're not.
And
What's
so
the
with
difference?
SP mixing, basically, it's lower energy for the orbitals?
Yeah,
or-
well, what
okay.
happens, because when you mix them, this becomes lower because that's more favorable because you have the favorable P interactions, so like these are in phase and these are in phase with that basically, so it's like super good. So that would be lower in energy. This anti-bonding orbital gets minimized because your electron density is on the outside. So even though they're out of phase, there's not as much electron density there, so not as bad.
Yeah, I was back there.
But then we have the swap, so now that means though that our p orbitals are more in phase, so they have a stronger bond, even though it's that through phase pi interaction. Then we pay the price of this essentially with our in phase bonding, but I call it non-bonding because our electron density is on the outside. But this is still
So that's
considered a
still a
bonding.
bond, but it's, okay.
Yeah, it's still formally bonding, so you still count it as a bonding, right, when doing our thing. But it's just the electron density is on the outside.
Yeah,
So,
okay, got it. That's what the SP is.
yeah,
So then,
so that swap happens, yeah.
so
So
then
it is,
so without the,
yeah, with no SP mixing, you just do two S orbitals, and then you go to your PZ signature. And then from there.
gotcha, okay.